Hi, welcome to chapter 11. This chapter, we will be covering the flexible payment design, and it's again, the chapter is from Huang's book. In this chapter, we're going to go through two major flexible payment design methods. The first one, we're going to be discussing the ASHTO design procedure that was developed in 1993 by the American Association of State Highway and Transportation Officials. And the second method that we will also briefly cover is the Aristotle Institute method that was also available for us, and we can use. But again, I'm going to concentrate on the first one, which is the most common one that most of the DOTs still use. Is the ASTO 1993. So let's get going.
So this method actually was based again on the empirical ASHO road test in 1960. It was mainly dependent on multiple factors that they tried back then the pavement engineers to include in the pavement design methodology. So they related the pavement design to reliability level, which means if I can design the roadway with high reliability at let's say 99% reliability, which means again most of the time that this pavement is going to last for what's intended to be. Let's say if I'm designing it for 15 years, it's going to last for pretty much for 15 years. But if I'm designing the pavement for with a reliability level of 50%, that means there's 50% chance that we're going to reach the 15 years design life, and there's 50% chance that this pavement will have premature failure. We also included drainage. How bad or how good is drainage in this location? We also included they included the climate factor, which was introduced in 1986 version. They also had the failure criterion, so it's the thermal serviceability, which I'm going to explain a little bit, which is called thermal serviceability PT. We have also ESLs. ESLs is equivalent single axle load. Equivalent single axle load, which basically they converted every axle or every traffic that they see to this equivalent single axle load, which is typically the 18 kips axle that's in 18 most of the 18-wheeler trucks, which is dual axle tire. So I'm gonna draw it to you here using this. So excuse me again for the drawing. I'm using my mouse to draw this, but basically the equivalent single axle load is two tires from one side, and I have two tires from the other side. So this is here the dual tire equivalent single axle load, and it has certain amount of load, which is about 18 kips. 18 kips, meaning that it's 18,000 pounds, which means actually every tire will handle about 4,500 pounds. So ESLs were used as a designing to design the pavement to failure as a failure criteria as a function of SN, the structural number, which I'm going to explain next lecture, the structural number for the subgrade strength, and the delta PSI, which is this change in the pavement serviceability index with time, and the reliability level. And then we came up with also solution for the structural number by spreadsheet or a nomograph, which again I'm going to explain next time. So after we collect all the inputs required for pavement design, we're going to enter a nomograph or a graph, long graph, to come up with what we call the structural number. The structural number eventually will be related to the thickness, the required thickness for each one of the layers in any pavement structure. And then we're going to again select the layer thickness for each one of these materials. A little bit of history here, the way it started back in the 60s. It was started in Ottawa, Illinois road test. As you could see, it's a long stretch pavement as well as a circular location here where this is trying to represent an exit or an entrance of a highway where low traffic will slow down and is going to introduce lots of shear stresses at the pavement at this location. So apparently the pavement design for this location here is a little bit different than the long stretch that we see on this highway. This is here when they started again back in 1961 when they started to compact the first layer. So they just picked one subgrade type, one single soil, Even again, we know that the soil here in Texas and even in East Texas is different than in West Texas, let alone how different it is from Arizona or Alaska. Yet again, at that time, it was very basic. They just picked one subgrade type and they went with it. And this is here the very basic equipment that they used to compact this subgrade type. And then this is here when they started the main construction of the full structure in the 1950s, where this is here they compacted the sub base, and this is here the bituminous concrete construction itself. So this picture here, the very top layer, at the very bottom layer actually, which is the subgrade, and the this is here the second layer, which is the compacting of a subbase. And then here we have the bituminous concrete layer, which is the top layer. Even the amount of traffic loading that was applied at that time, it was very small compared to what we have now. Yet they tried to do it the best they can using uniform loading. For example, this first one is here is a truck. They put a uniform concrete um, load, so it's uniform. They know exactly how much load is on this axle, and they know how much load is on that axle. Same thing with bigger trucks, all the way to the old style of the 18 wheelers back then in 1961. But as you could see, they try to put uniform load, so they know once we apply this uniform load, and all what they did afterwards, they just keep driving these trucks over and over on those sections until it fails. So it's pretty much an accelerated testing to know and to apply the amount of easels, the equivalent single axle load that will be experienced by any road in 15 years. They did it in like 6 months in order to accelerate the testing and to know how much this pavement will last before it starts to fail. However, again, looking at these simple pictures here, the amount of traffic application that was done at that time was very limited. You could tell these are the amount of axle load repetition that they applied. And if you really want to extrapolate this to our current time traffic, this prediction can go three different projections. I can make use of this data and I say, you know what, the amount of traffic based in the 60s is going to have a linear growth, it's going to continue as is, and I'm going to have projection A. Or I can have projection B, which is the amount of traffic is going to go this way, but it's going to increase and then it's going to stabilize again. Or in other cities in the States nowadays, we have amount of traffic here and go all the way to projection C, which is just exponential increase of traffic with time. So this gives us again an indication that it has some limitation of the prediction, but still again it still serve and give us a good estimate of what's the required pavement thickness that we need. But just keep in mind that it all depends on the traffic projection that happens at our current design. It's way different than what they did in the 60s. So the empirical performance equations, again, that were obtained from the AASHTO road test used in 1993 AASHTO, but again, were modified with time and extended to make them applicable to other regions. As you could tell from the beginning, in the 60s, they did only one subgrade, only one location, but then 30 years later, they did multiple locations, multiple traffic loading to have more robust way of analysis. So let's start some of the design consideration that we need to understand before we get into this nomograph to get the structure number and therefore the thickness of each layer. The very first one is the what we call a performance period. There's something called performance period versus analysis period. So what's the difference? So performance period is actually refers to the period of the time that an initial pavement structure will last before it needs rehabilitation. So the minimum performance period is actually the shortest amount of time given at a given stage that should last. So for example, it may be desirable that the initial pavement structure will last for 10 years before some major rehabilitation operation will be performed. After those 10 years, I'm going to apply another 2 to 4 inch overlay that's going to last me for another 10 years. and this goes on until I reach the end of the analysis period. The analysis period actually refers to the period of time for which the analysis is to be conducted. The analysis period is some sort of analogous term for the design life used by the designers in the past. So what does this mean? That means the analysis period is actually a longer period of time that includes multiple performance periods. So that's why analysis period is going to be higher or equal to the performance period. So let me explain how can this be. So let me try to draw this for you here. This is here time t, and this is here the performance or the pavement performance. So let's say with time, as we got to know from last lecture, pavement does fail with time. So let's say I constructed the pavement and then start from a high value, and with time it went down until at this point. Now I'm going to apply something else, some sort of rehabilitation. Let's say this lasted for uh, 5 years. And then at the end of the 5 years, we said, well, you know what, we need to do some maintenance. I'm going to apply maintenance. Let's say a 2-inch overlay is going to pump up the performance of the pavement. Not again, not to the original condition, but at least a considerable improvement. And then this 2-inch layer is going to last maybe for 7 years before it reach another failure. And let's say at this point we didn't have enough money to do another 2-inch layer. We did a very minimal surface improvement that's going to pump up the surface this much, and then in 2 years, let's say this is here 7 years, and this here the minimal, let's say seal coat, is going to last for 3 years before it reach perfect failure or terminal failure. And now at this point we need now to rip off the entire structure and do a major reconstruction. So in this picture here, we can understand the two things, analysis period and performance period. The first 5 years, this is the first performance period. So this is here, we call this is performance period 1. And then we did a 2-inch overlay and we had a 7-year performance. So this is performance period 2. And then we have a seal coat that lasted for 3 years. And this here we call it performance period 3. If I sum up all the 3 performance periods, I will be able to get the entire analysis period. This is here the analysis period, which is in this case is again a summation of performance period 1 and performance period 2 plus performance period 3. So in this case, the analysis period would be 5 plus 7 plus 3, and that would give us 15 years analysis period. So that's why we say the analysis period is most of the time is higher than any performance period. The only time that they are equal to each other, if we do one strong structure from the very beginning and we let this structure last for 15 years until it reaches failure, and then we have to rip off the whole structure and then start from scratch. So in this case, there will be the one performance period, let's say it's equal to 15 years, which in this case, the performance period will be equal to the analysis period, which is equal to 15 years. I hope this is now understood. So what are the typical analysis periods based on the AASHTO recommendations? So for any high volume urban roadway, which means again most of the interstates, we design them to last for 30 or 50 years. I can't afford do a major reconstruction ripping off the whole structure every 5 or 10 years. So for high volume urban roads, the analysis period will range from 30 to 50 years. For high volume rural road, it can be as low as 20 and it can go all the way to 50 years. For low volume paved roads, the standards are less, and and typically we design them somewhere between 12 to 25 years. And for low volume aggregate surface, they range from 10 to 20 years. Another design consideration that we're going to use in the nomographs next lecture is the pavement performance. A pavement performance is designed and is quantified by what we call serviceability index. Serviceability index, it ranges as it's a scale, how good is the pavement from 0 to 5. 5 is the best pavement performance, and 0, this is pure failure. And typically we don't wait till 2, we don't wait till 0 actually, the lowest would be 2. But the PI, this is what we call the initial serviceability. So for any pavement, as you recall from last lecture, again with time, this is the pavement serviceability or pavement performance. So we start from this index in particular start from 5 and goes down. So the highest is 5. This is a very theoretical number. Typically, for even brand new road, for flexible pavement, the initial serviceability is equal to 4.2. So for flexible pavement, again, we start from 4.2. This is the initial serviceability until we reach failure. So the next question is how to define failure based on this scale. This is what we have here for the next slide is failure. It actually depends on the functional classification of the roadway. If it's a very important interstate roadway, we're not gonna wait until this structure just crumble. We're gonna call the terminal serviceability equal to 3. Again, if I draw the same graph, if I have a perfect road, which starting from 4.2, flexible pavement start from 4.2, once I reach 3, this is here 3, I'm gonna need to go to the field and do some major maintenance at this roadway if it's an interstate. If it's a principal arterial, I can wait until it's 2.5. So the terminal serviceability, it can be 2.5. Principal arterial, like again, it can be again smaller roadways. For example, in the city of Tyler, we have loop 323. So I can wait until the performance of the pavement is 2.5. If it's a collector or a local street like Varsity Drive or Patriot Drive, I can wait all the way to 2 as the terminal serviceability. So this graph, I can allow it to go to degrade all the way to 2, nothing less than 2. Another term, and then so we have the initial serviceability, which is PI, and the terminal serviceability, which is PT. The difference between the two, which is what we call now delta PSI, is PI minus PT. This is the difference between the initial serviceability and the terminal serviceability. So let me ask you this. For example, if I have an interstate 20, what would be typically the delta PSI for a pavement? So for a perfect pavement, it's 4.2 minus PT. PT, again, based on interstate, is 3. So terminal serviceability would be equal to 3. So therefore, the delta PSI would be equal to 1.2. For a small road, let's say again Varsity Drive or Patriot Drive, is going to be actually 4.2 minus the terminal serviceability, which again I'll get from here. Collector or local, it's 2. So I'm going to go here and say 4.2 minus 2, and that will be equal to 2.2. The delta PSI will be equal to 2.2. Next is traffic. Traffic, as I briefly mentioned at the beginning, when it comes to flexible pavement design using the Ashton 1993 method, we need the cumulative expected 18 kip equivalent single axle load. ESLs is equivalent single axle load. We need to convert everything to this ESLs, and we need to know how much cumulative number of these ESLs over the design or over the analysis period. It all depends on the axle type. If it's a single axle or tandem axle or tridem axles, it also depends on the axle load. How much does each one of these observed axle load we have? We can have 2,000 pounds per axle, which is typically in most of our small vehicles, and we can have up to 90 kips, 90,000 pounds per axle. And of course, it depends on the delta PSI and the terminal serviceability index. So it can depend on if it's 2, 2.5, or 3. So the traffic and the design lane, because the traffic typically is collected over the entire structure first in the two lanes, but then we need, which is this is here the observed amount of traffic, then we need to multiply it by L and multiply it by D. What are these two? L, this is the let's start with the D. D is the directional distribution factor, which is generally 50% or zero point 0.5. What does this mean? Let's assume here I have um, two two-lane highway per direction. So I have two lanes here, and I have two lanes in the opposite direction. So if we measure the amount of traffic, and the amount of traffic, which is W18 or easels, is equal to 2000 easels. I need to know how much traffic on one lane to design this lane, or the worst lane, out of the whole structure. And once I design the pavement on this structure, I'm going to generalize it on the entire structure. But in order for me to design this lane in particular, I need to know how much traffic out of this 2000. So this 2000 is not going to be on this single lane. First, I need to multiply this 2000 by D, directional factor, or directional distribution factor, which is 0.5. So I'm going to multiply this by 0.5, and this is going to give me now, and there is 1,000 easels per direction. So within this direction here, I am experiencing a 1,000 easels, but now I need to multiply this number further by a lane distribution factor, because not the full amount of easels will be on this lane. So the lane distribution factor, if it's one lane per direction, there is no need to do the lane distribution factor, because if it's just one lane per direction, that 1000 will be experienced by one lane. That's why it's 100%. But if I have two lanes per direction, the lane distribution factor is somewhere between 80 to 100%. You may wonder why. Can't we just say half of the 1000? That's if you want to do half of the 1000, you're not really actually including any factor of safety. Typically, the outer lane, the right lane, handles much more traffic than the passing lane or the left lane. So that's why if we have two lane structure, two lane per direction, we multiply the 1000 by 0.9. Which is the average between the two numbers here. If I have three lanes per direction, the lane distribution factor will be somewhere between 60 and 80%. And if I have up to four lanes per direction, I still consider the right lane will handle somewhere between 50 to 75% of this amount of traffic. So as continuation related to the easels, again, we need to use the total easels over the analysis period if the pavement design for the analysis period without any rehabilitation or resurfacing. So if I get, what does this mean? It means if I'm designing, if I know that the analysis period will be 20 years, and if I'm designing this structure from the very beginning that for certain thickness that will last for 20 years, then I need to include all the easels projected for this 20 years. But if I'm gonna do a stage construction or rehabilitation or resurfacing, I need to account for the amount of easels that's gonna be enough for the first stage. For example, if I want to do a 4-inch structure at the beginning, I'm going to have easels that's going to last for, let's say, 10 years, enough for this initial structure, and enough for this initial stage of construction. So just bear in mind, again, what type of design you're considering. When it comes to the material considerations, so far we talked about serviceability index, PT, thermal serviceability, initial serviceability. We talked about traffic. Let's talk about materials and how are we going to use the materials in this nomograph next lecture. Materials consideration, we have soil strength, which is measured as MR, which is the resilient modulus, something similar to elastic or dynamic modulus, or resilient modulus, or in physics it's actually just elastic modulus. We also are going to get to know what's the layer coefficient for the hot mix asphalt layer, the base layer, and the sub-base layer. And also we need to know what's the drainage coefficient for each one of the layers in the structure. So let's start with the first material consideration for the effective road bed soil resilient modulus. What does this mean? So the subgrade strength is typically measured by the resilient modulus, which is it's a lab resilient modulus test. It has an ASHE standard T307. Look it up if you'd like more information. But it's actually a test that's performed on representative samples in stress and moisture conditions that simulate those of the primary moisture season that we see in the field. So trying to simulate what's going on in the field. So this resilient modulus test is a very sophisticated test that we're going to explain in other classes, but it can be estimated from a simpler tests. There's a test called CBR test or an R value test. So once if you're able to run any of these two tests, you'll be able to correlate them back to the resilient modulus test that you need to know. So for example, if you have a CBR value, California bearing ratio, look it up. And we're going to try to touch upon it a little bit, but it's not a requirement to know much detail about it in this class. It's going to be given to you if you need to use it in an exam or in homework. If I have the C-bar value to the power 0.64 times 2,555, I'll be able to get the resilient modulus in PSI. Or if I know the R value, another test multiply by 555 plus 1155 to get the resilient modulus for that sample. The question here is whether you're going to do a resilient modulus test itself or CBR on R value. We need to understand that the resilient modulus or the modulus of the soil would vary by season. In a wet condition, again, if it's rainy condition, the soil will be very weak because it's very moist. If it's in the middle of the summer, the water will evaporate with time. It's gonna start to gain some strength. And in some conditions and some locations in the middle of the winter, when it's freezing, the water will be frozen inside the soil and it's gonna pump up the overall strength of the soil. So which value should we consider when we're designing pavement structure? One of you may say, let's pick the lowest value to be conservative. But if you end up doing this, you're going to end up with a very thick structure on top of the soil because you're now downgrading the strength of the soil in the rest of the season. Another will say, how about the maximum value or somewhere in between? I would agree with the one that said it's yes, somewhere in between. And this is what we call the effective road bed resilient modulus soil. It's an equivalent. This is an effective resilient modulus. Basically, it's an effective or equivalent modulus that would result in the same amount of damage if the seasonal modulus values are actually used. Let's take a look at this picture here, which I just explained it in a few minutes ago. Resilient modulus, again, in the winter, January and February, is very high, and sometimes it's frozen. Even if it's not frozen, it's close to a freezing condition where the water inside the soil is pumping up the resilient modulus values. And then once we reach February, March, where this is spring, water now is going to start to thaw, and we're going to experience a sudden drop in the resilient modulus somewhere in mid-March, early April, where we're going to see now the lowest resilient modulus value. And then with time during summer, now the water starts to evaporate. So it's moving now from solid state to liquid state. Now it's going to evaporate, where now we're going to start to see gain in resilient modulus with time during summer. And by the time we reach fall again, October, November, we're going to start to see more water penetrating through the soil again. We're going to see a drop, and until we reach January, where it's going to peak up again. So the question is again, which value should I use? And the method that I'm going to explain it to you in a second here is actually what we're going to try to do is what we call the effective resilient modulus. We're going to try to come up with a number that is that's going to give us the same amount of damage, equivalent or equal damage for all the months of the year. So for example, if I apply a load on this soil at a high in January, the damage will be very minimal. While it's in March, if I apply the same traffic loading on this soil on March, I'm going to have a very minimal, a very high amount of damage. So the effective resilient modulus, we're trying to pick up that value to give us an average damage across the board. So, and that's here the steps. How can we get the effective roadbed soil resilient modulus? First of all, we need to divide the years into periods with different resilient modulus based on the soil moisture as well as the temperature or any non-destructive testing, NDT, non-destructive testing. So once we divide the years, we can divide the years into 4 seasons. So we go to the field 4 times a year, or we can do it every month. When we have 12 measurements per year. Then we need to determine what we call the relative damage for every period, let's say for every month. So I'm gonna go to the field, I'm gonna measure the resilient modulus, let's say in January. I'm gonna plug it into this equation, resilient modulus to the power minus 2.32 times 1.18 times 10 to the power 8 to get the amount of damage, relative damage for the month of January. I'm gonna wait for a month, go into February, do the same thing, get the damage for the month of February. And I'm gonna get the damage for all the 12 months. Once I get the damage for every single month, I'm gonna sum them up and divide them by how many periods, which is in this case 12 months, to calculate the average relative damage. The average relative damage will be equal to all the damages for all the months over 12 to get the average relative damage. Once I do this, I'm gonna now find the effective resilient modulus using the same equation, but it's flipped. So now I'm having the resilient modulus in one side and the damage on the other side. So if I get the average relative damage, which is again the summation of all the months over 12, raise it to the power minus 0.431 times 3015, I'll be able to get what we call the effective roadbed resilient modulus for this soil. Let's have here an example so everyone would be on the same page how to understand this concept. So here we have 12 readings from January, February, March, all the way to December. And what we did, we measured what would be the soil modulus per month. As you could see in January, as we explained to you previously, January was one of the months that the water might be freezing in the soil, and that's why the resilient modulus is very high, 20,000 psi. February, it may stay as is. In March, all of a sudden, now we are getting into the spring where the water is thawing, and now we reach one of the lowest values for the resilient modulus in the month, which is in March, 2,500 psi, very low. In April, it started to pick up 4,000, stay 4,000 in May, June, July, August, September, October, they are about the same, 7,000. Start to rain again in November, and then when the fall start to pick up, and now we have reduced amount of resilient modulus, 4,000. And in December, when we get to the freezing zone again, it's gonna pick up again. So how can we come up with this effective roadbed soil resilient modulus? Is we need to follow the steps that we mentioned here. So for every one of these months, we have modulus. We need to plug it to this equation to get the relative damage for every month, and that's what we did here for this column right here. So let's pick the month of January. So it's this equation right here. Where did we get this equation from? It's from here, this one right here. So it's 1.18 times 10 to the power 8 times the modulus of this month, which is 20,000, to the power minus 2.32. So we get a very small amount of damage for this month, 0.01. Now, if I want to pick March, for example, it's the same, 1.18 times 10 to the power 8 times 2,500 to the power minus 232 at minus 2.32. I'll be able to see the highest amount of damage is in the month of March, which is 1.51. So the idea here, you're going to need to do this equation for 12 times. Then you're going to sum them up. You're going to sum up all the damages, which is 3.72 right here. And then you're going to divide them by how many months or how many readings do you have? 12 to get the average damage per month. Average damage is 0.31, which is in this equation here, this step, calculate the average relative damage. Next, once you get the average relative damage, you're going to apply this simple equation here to get the effective road bed modulus. So 0.31, you can apply it in here to the power minus 0.431 times 3015, and here you go, you have the effective road bed resilient modulus equal roughly about 5,000 psi. Not 20,000 like in January, not 2,500, which is in March, somewhere in between. It's 5,000 psi, where this number, if you were to apply it, we're going to have equivalent amount of damage for every single month. Next part of the design consideration is what we call the layer coefficient. This is layer coefficient. Every one of the layers, remember, for any pavement structure, as we talked about last time, we have the top layer, the HMA, the hot mix asphalt. On top of this, we have a base, and then we may have a sub base, and all this on top of the subgrade, which is the technical word for the soil. So each one of these layers has a layer coefficient in the pavement design procedure. Layer coefficient is nothing but a measure of a relative ability of a unit thickness of a given layer to function as a structural component of the pavement. In other words, how strong this layer coefficient is, give us an idea how strong is this layer. It's actually where these numbers were determined based on the Ash-to-Road test, and we have correlations between the material properties versus the resilient modulus versus the load coefficients. So again, in the ASHA 1993, the notations MR and resilient modulus. So I'm gonna talk to you about this next lecture. It refers only to the road bed soil, where E1, E2, E3 applies to the HMA base and sub base. So going back to here, for the top layer, we call it E1. How strong is this layer? To get the layer coefficient, we need to relate it to the modulus of the top layer, which is E1. And the modulus of the second layer, we call it E2. The modulus of the third layer, we call it E3. The modulus of the last layer, we don't call it E4, we call it MR, resilient modulus, like what I showed you previously. So this is what this slide is all about. So let's get going with the first layer coefficient. The top layer, we call it layer 1. That's why the asphalt concrete surface course, we call A1. To get A1, the layer coefficient for the top layer, we get it from figure 11.27. And there's also this chart relates the layer coefficient of the dense graded hot mix asphalt to its resilient modulus at 68 degrees Fahrenheit. So this is the graph that you're going to be using. Let's assume I have a modulus of 450,000 psi. So what you need to do here, you're going to look up the 450,000 psi in the x-axis. This is the elastic modulus of this layer. You're going to go all the way up to hit the figure, and then you're going to draw a horizontal line to pick the A1, which is the structural layer coefficient for the top layer. And in this case, A1 will be equal to 0.44. Very simple, very straightforward. All what you need is the modulus for the top layer. For the second layer, the granular base course layer, if it's untreated base, what I mean by untreated, most of the time the second layer, the base layer, is basically crushed aggregates, and we crush it, compact it very well, especially if the aggregates are very strong. If the aggregates are not strong, we treat it. What does that mean? We add bitumen, we add asphalt, liquid asphalt to strengthen the base layer, or sometimes we add cement treatment, or sometimes we add lime. So if nothing was added to the base, we call it untreated base. Untreated base, we use figure 7.15a in your textbook, or you can use this equation right here. So A2, the layer coefficient for the second layer, is 0.14 times the modulus of this layer over 30,000. So for example, for the Ash-to-Road that was performed back in the 90s, A2 was 0.14. Where did they get this from? E2 was 30,000. So 30,000 over 30,000 times 0.14. So really, any layer now that we try to characterize, we compare it to this layer that was done back then. So if it's more than 30,000, so we're going to divide it by 30,000, multiply it by 0.14. If it's less than 30,000, divided by 30,000. So it's a ratio comparing it to the original granular base course that was done back in the 90s. For bituminous treated, we have another figure, figure 7.15b. For cement treated, we have 7.17c. For the third layer, A3, this is a sub-base course. We have this equation right here, 0.227 times the log of E3 minus 0.839. For the Astro test, A3 was 0.11 because E3 was 15,000 psi. Last thing here I want to leave you with before I let you go is the drainage coefficient. So far we've talked about, again, thermal serviceability, we've talked about material characterization, we talked about layer coefficients, we talked about traffic. Last thing is drainage, the drainage coefficient. Drainage coefficients we call Mi or M1, M2, M3. This coefficient actually it's used to account for the loss of strength of pavement under moisture effects. And ASHTO uses drainage coefficients again to reduce the strength of certain layer if the drainage is not that good. So drainage coefficients M2 and M3, we do not have an M1 for the top layer. The hot mix asphalt layer is considered a strong layer. It doesn't again there is no drainage coefficient for it, but there is a drainage for the base and the sub base layer. How can we get these two? The drainage coefficient depends on two factors. The first factor is the quality of the drainage, which is the time required to remove most of the water from the surface. So it's all about how long does this water, once we have a rainy condition, how long does this water stays on the surface? If the water dissipate in half an hour, this is a good structure. Therefore, I'm not going to have a thick structure if the quality of drainage is very high. If the water sits on the surface after a rainy condition for 2 days or a week, this is a bad structure, and then the M, which is the drainage coefficient, will be very low, indicating that I need to have a thicker structure to handle a bad drainage condition. The other factor that the drainage coefficient depends on is the percent of the time the pavement is exposed to moisture level approaching saturation. For example, again, how many months of the year we have the structure is saturated. Is it 1 month, 2 months, which is a good thing, or is it 10 months out of 12? So table 11.20 on page 518 will explain this to you here. So the very first portion of this table, it talks about the quality of drainage. How can we quantify that? So if I have, again, if the water is removed or the water doesn't stay on the surface for more than 2 hours, this is an excellent drainage. So 2 hours, it's an excellent drainage. If the water stays for 1 day before dissipate, this is a good drainage. If the water sits for a week, this is a fair drainage. If the water sits for a month, which is really bad, this is poor drainage, especially if it's, again, if the water doesn't drain at all, this is very poor drainage. So this is here when it comes to the quality of the drainage. The rest of the picture is actually in this table right here, which is the first portion of it. This is the quality of the drainage, which we just talked about. Again, 2 hours excellent, 1 day good, 1 week is fair, but also the percentage of the pavement that the structure is exposed to moisture levels approaching saturation. If it's less than 1% of the year, you're going to pick these numbers, or this column right here. If it's 1 to 5%, it's this. If it's greater than 25%, it's that. So let's have a simple example here. So if I have a pavement that's designed with fair drainage, and the moisture drain, which fair meaning that the moisture will drain within 1 week, and 2 months of the year, are likely to be saturated condition. What is M2 and M3 in this case? So first, it's a fair drainage. That means it's going to be within this line. And then I was told that I have 2 months out of the year. So 2 over 12, I'm going to use here my calculator. 2 over 12, that's times 100, that's 16%. 16%, so it's not this column, which is less than 1%. This is 1 to 5, 5 to 25, which is the 16% goes within this range. So somewhere the drainage coefficient for layer 2 and 3, it will range from 0.8 to 1 in this case. With this, I would like to stop right here. And again, next time we're going to talk about a few other factors that's going to get into my pyramid design, and then we're going to get into the nomographs to get the structural number, and afterwards we're going to get the thickness of the thickness needed for each one of the 4 layers or the 3 layers on top of the subgrade. With that, again, thank you, and we'll see you next time. Bye bye.